Welcome, this is Dr. Plague, and in this video we'll have some fun designing and building up the Plague Mark I homemade CPU. This will be the first of a series of CPUs that I will be designing and building up, and they will become more complex and functional as we continue in this series. I will explain a little bit about what I plan on accomplishing in the design, then I'll simulate the design, and finally build it up on a breadboard. I'll go through a few iterations of this processor to help spark some ideas and creativity. I'm going to show in the first iteration that you cannot always trust a simulation. So I will be simulating something that appears to work, but as I'm sure we'll find out, it will not function correctly when built up on a breadboard. The purpose of this CPU is not to astound or wow you, but simply it is to demonstrate a very simple and basic concept in CPU design. Some of you may even argue over whether or not the Plague Mark I is even a CPU. So let's take a look at this old dictionary of computer terms that I have. This book is from back in the 80s, so we'll get a good idea of what CPUs used to be thought of as. Not that it's any different from today. Let's see. Here it is. The CPU, Central Processing Unit, is the part of the computer where arithmetic and logic operations are performed and instructions are decoded and executed. The CPU controls the operation of the computer. A microprocessor is an integrated circuit that contains a complete CPU on a single chip. So according to that, a microprocessor is contained on a single chip. That's the reason I'm not calling my design a microprocessor, but rather a CPU, since they can be built discretely or by using individual parts. Also, the definition mentions a CPU performs arithmetic and logic operations, but doesn't state that a CPU necessarily needs to perform those functions. The part that I'm concentrating on is that instructions are decoded and executed. The Plague Mark I will be so simple and basic that all it will do is point to an instruction in memory, then basically decode and execute it. And these instructions will be extremely simple. All this processor will be able to do is either output a value or jump to another memory location. I will use the output value to drive some LEDs. This processor is going to be so simple that I'm going to start out designing it with a single 74 series logic chip. I'm going to use a counter, and this will serve several purposes in this design. First of all, it's going to act as a register. That is, a register that holds the value of the instruction pointer, which I will abbreviate as IP. Don't get this confused with Internet Protocol. IP will usually stand for instruction pointer in my videos. If you're not familiar with an instruction pointer, it is simply a value that represents the memory address of a CPU instruction in memory. And in my case, I'll use a flash chip to contain the CPU instructions. So I'll put an instruction into the flash memory that we want the CPU to execute. When the instruction pointer points to that instruction, the CPU will execute it. Perfect. Another purpose of the counter will be to increment the instruction pointer so we can continue executing CPU instructions in an ascending sequence within the memory. We'll also use the counter to execute instructions, since the instructions will be able to change the counter value. So, for this first iteration of the Plague Mark I CPU, a 74 series counter IC will be used basically as a single chip CPU solution. Let me draw this up for you. So, let's say we have a 74 series counter IC right here. This will be a single chip solution. The value of this counter will be sent to the address inputs of a flash memory chip. And bear in mind that the flash memory chip is not part of the CPU itself. It is external to the CPU. Just like if we had an 8088 microprocessor, we would need to connect memory up to it. And just like with the 8088, we need to connect a clock signal up to the counter to keep it moving along from one instruction to the next. Now, this flash memory chip will hold instructions that tell the counter to either continue counting or reset back to address 0. Each byte at each address in the flash memory chip will have 8 bits of information. And I'll just use 1 bit to indicate whether or not we reset the counter. And we can use the other 7 bits to drive some LEDs. So this line being fed back to the counter is being used as a very basic decoder. And the reset input of the counter is used to execute the instruction. So simple. So let's build this up in a simulator really quick to see how it functions. I'm using DigitalWorks, and I have a video that shows how to use this free simulation software if you are unfamiliar with it. The link will be in the description. I'll add in a memory chip to contain our code. I'll select one with 4 address lines and 8 data lines. And I'll connect the chip select line to ground to keep it continuously enabled. I'm going to use a 74393 logic chip for the counter. It contains 2 4-bit binary ripple counters, and we can cascade them to create an 8-bit counter if desired. But I'll just use 4 bits for now. I'll just use the upper counter shown in the datasheet right here. Pins 3, 4, 5, and 6 contain the counter value, so I'll just connect those up to the address line inputs of the memory chip. Pin 1 is used to clock the counter, so I'll just add in a clock signal and connect it up to pin 1. Pin 2 is the master reset, so I'll just connect the most significant bit of the memory chip's data lines up to that. What this means is that the most significant bit of the CPU instruction will reset the instruction pointer back to 0 if the bit is set to a 1. This is because the master reset pins of the 393 chip are active high. FYI, when we build this up on a breadboard, we'll want to terminate all unused inputs to either power or ground directly or through resistors. But in the simulation, I won't worry about that. I also won't be connecting power and ground to the chips in the simulation, since the simulator doesn't need it, and it helps to make the diagram less cluttered. Now, I'll connect the rest of the memory chip's data lines to LEDs for our output. So, this 393 chip is basically our CPU, and the rest of this circuit is the simple computer that we've built, if we can even call it that. Now, we have 2 basic instructions that this CPU can execute. Out, which just sends the 7 least significant bits to the LEDs, and reset, which resets the IP register. The most significant bit of each instruction will be the opcode, and the 7 least significant bits will be the operand. For the out instruction, the opcode will be 0, and the operand will indicate which LEDs to light up. And finally, for the reset instruction, the opcode will be 1, and the operand value won't matter. Let's now write some code for the CPU to execute. So I'll just double-click on the memory chip to open up the memory contents here, and I'll use the binary mode. What I am going to do is to write some code that will give us sort of a Knight Rider type effect. I'll create an LED sequence that continues to move back and forth. This will kind of simulate the front lights on the Trans Am in the TV series Knight Rider, if you're old enough to remember that. However, I believe there were 8 lights in that sequence. Oh well. We have 7 bits connected to 7 LEDs, so I'll turn on the first LED in the first instruction byte by setting the first bit to a 1. And notice that I'm leaving the most significant bit as a 0, which is the out instruction, since I don't want to reset the counter yet. Now, I'll just continue adding instructions to turn on the LEDs in the sequence that I desire. Notice that all the 1s in this data show the order that I want to light up the LEDs. Once I'm done entering the sequence that I want to create, I'll just add an instruction to reset the counter. In other words, I'll set the most significant bit to a 1. There, let's try this out. First, let's make sure that the clock speed is set to something not too fast and not too slow. I'll choose 5 Hz. And here we go. Look at that. It seems to work just fine. But sometimes looks can be deceiving. Even though I haven't built this up yet, I'm very doubtful that it will work in real life. There's a reason I do not think this will work. See if you can figure it out while I build this up and test it out. I'll be using this here flash memory chip, so let's program it with the same code used in the simulation. And I'll use this here homemade programmer that I built in previous videos. I'll put a link to those videos in the description. I'll first erase the flash chip, then start adding the hexadecimal values to match the simulation. Let's dump out the first 16 bytes. Yeah, that looks about right. By the way, this isn't going to look very pretty. It's just a temporary circuit, so I don't care about the neatness. I'll connect power and ground to the flash chip. And since I'm only using 4 address lines, I'll connect the rest of the address lines on the flash chip to ground and just leave address lines 0 through 3 for the counter to connect to. I'll also connect the write enable line to VCC since we're only reading data from the chip. And I'll connect both the output enable and chip enable to ground to enable the output. I'll add the 393 counter chip to a separate breadboard to help indicate that the flash chip, LEDs, and such are not part of the CPU. It'll also make it easier to pull out the flash chip for reprogramming if it's not sandwiched between other chips. I've connected power and ground to the 393, and now I'll connect the counter output, pins 3 through 6, to address lines 0 through 3 on the flash memory chip. And of course, I'll connect the most significant data line from the flash chip to pin 2 of the 393 counter chip. I'll also terminate the unused inputs of the 393 to VCC. Now, I'm actually going to connect the 7 least significant flash data lines through a 74541 buffer to the LEDs, so we have more drive current. And you can see that it can source or sync 25 milliamps per output pin. And I'll use 470 ohm resistors in an array to limit the current to the LEDs. For the LEDs, I'll just add in this here bar graph style LED so the pin spacing lines up well with the resistor array. And for the clock signal, I'll just connect pin 1 of the 393 up to a waveform generator set up to provide a 0 to 5 volt square wave at 5 Hz. Then I'll just connect up the power supply. Now, this should be the same basic circuit that I had connected up in DigitalWorks. Let's power this up, apply the clock signal, and see what happens. Well, that's not quite what I was expecting. It is working. Oh, man. Well, let me try another flash chip here. This one is an older Atmel chip, and I've programmed it the same as the first flash chip. Now, let's swap this flash chip out. Not quite working now, is it? This kind of shows you that we cannot always trust a simulation. We really need to build up our designs to be able to fully test them out. So, what's the problem? Let's look at Figure 5 in the flash memory datasheet to see why I thought this was not going to work. This is the read cycle timing diagram. When we output an address to the flash chip, the data is valid in this time period here. But when we change to the next address location, we have a small period right here where the data is not valid. During this small period, we could get erroneous data on the data lines, which in turn could reset the counter when we're not expecting it. That can help explain why this isn't working, or at least with the second flash chip. Also, we have the issue of not counting in gray code, which could be a problem, and I'll look more at gray code in another video. So, that did not work out very well, and there are a number of ways we could try to fix this. We could add additional ICs to help us, Or one thing we could do is look for a different type of counter IC if we want to keep this a single chip solution. What we need to find is a counter that has a synchronous reset. And what that means is that the counter will only reset back to 0 when the clock signal transitions from low to high. So, depending on the signal at the reset pin, the low to high transition of the clock signal will either increment the counter or reset it back to 0. Once the counter either increments or resets back to 0, then the flash memory will start transitioning from a valid data output through an invalid data output to its next valid output. So, what counter chip can we use? How about a 74HCT163? The only problem with this chip is that it's only 4 bits. So, we would need 2 chips to create an 8-bit solution, but we were only using 4 bits anyway. So, let's delete this 393 chip and pull in a 163. Be aware that this is a modified 163 macro, since the original 163 in DigitalWorks is buggy. I'll leave a video link in the description on how to fix it if you're using DigitalWorks. The outputs are on pins 14, 13, 12, and 11. The clock goes to pin 2 and reset goes to pin 1. And we need to pull pins 7, 9, and 10 high in order to count. Now, if we try running the current code, it doesn't work, and that's because this counter has an active low reset, unlike the 393, which was active high. This means the opcode for the out instruction is 1 instead of 0, and the opcode for the reset instruction is now 0. So, we need to go into the code and invert all the most significant bits. Now it seems to run. But since the reset is now synchronous, it takes a clock cycle to execute. So we need to add in the LED output to the reset instruction. The operand for the reset instruction now sets the LEDs. And I'll just add a reset to the second to last instruction to use its LED output. Then I'll delete the previous last instruction. Perfect. Let's build this one up. I'll first reprogram the flash chip, and I'll use the Atmel since we know that one did not work with the previous circuit. Now, if we look at the datasheet for the 163 counter, we can see that this counter is presettable, and I'll take advantage of this fact to load in the address of 0 when we first power this thing up. This will be one way we can reset this processor during power-up and still maintain a single chip solution. To do this, I'll just tie all the preset inputs to ground. Then, just connect up a capacitor from the parallel load enable pin to ground, and a resistor from that pin to the clock signal through a diode like this. I'll choose some large values to get a slow charge of the capacitor, maybe 100k ohms and 1 microfarad. This will take a short amount of time to charge up the cap from the clock line. So for a short period, the signal on the parallel load enable pin will appear to be low, which will load in the address of 0. Once the capacitor charges up, then the 0 address will no longer be loaded. I'm using the clock signal to charge up the cap since the parallel load is synchronous. And if there is no clock signal, then the capacitor can't charge up. If there's no clock signal, then we can't clock in the preset address value of 0. I'll be applying power before turning on the waveform generator to clock the counter. So I need to make sure the capacitor doesn't charge up until I turn on the waveform generator. The capacitor will affect how slow we can run this, but I won't be running this slow enough to cause erroneous resets. Now, admittedly, this is kind of a wonky way of doing this, and I'll fix it in the next iteration, so just bear with me for now. Okay, let's apply power and clock. And it starts out correctly by lighting the least significant LED first after the clock is applied. And we get the desired sequence. Excellent. Here's a quick scope trace of the capacitor circuit on the parallel load enable pin and how it relates to the clock signal. So you can see how it charges up once the clock signal starts up. Then the diode stops it from discharging when the clock goes low. Crude, but it does the trick. Now, let's play around with this a little more. One thing we can take into account is that the 163 chip is presettable. So, let's see if we can create a CPU instruction that allows us to jump to any accessible memory address. And since we'll be able to jump to any location, we can get rid of this reset instruction, since we could just jump to location 0 now. I'll just replace the reset instruction with a jump instruction. So I'll use the lower 4 bits, aka lower nibble, of the CPU instruction to indicate the jump address. And I'll send those bits to the preset inputs of the counter, pins 3, 4, 5, and 6. And I'll just need to move the most significant bit from the reset line to the synchronous parallel enable input. And of course, pull the reset pin high. Now the instructions have a slightly different format. We now have the single-bit opcode and 2 operands. The first operand is a 3-bit output value, and the second operand is a 4-bit address value. The out instruction will retain the opcode value of 1, and will use the first operand to send a value to the LEDs, while the second operand doesn't matter. And the jump instruction will contain an opcode value of 0, and it will use both operands, the first for the LED value and the second for the address to jump to. Let's write some code to light the first LED, then start toggling the other 2. So I'll turn on the first LED for the first 2 instructions. Then also turn on the second LED in the next instruction. Then finally, switch the second LED to the third LED in the last instruction, and jump back to address 2 to keep toggling. Cool. Let's build this up on a breadboard to see if it works. Again, I'll first reprogram the flash chip. By the way, I'm going to swap out the 74163 chip with a 74161. The only difference will be that the 161 will have an asynchronous reset. Therefore, I can connect up the capacitor circuit to reset the counter to 0, and we don't need to worry about whether or not the clock starts up, so I can charge the capacitor with VCC instead of the clock signal. This is a much better solution than what I had before, since the frequency of the clock signal will no longer affect the capacitor charge circuit. Okay, let's wire the rest of this thing up. And if I apply power and clock, this appears to work just like the simulation. And you will notice that as soon as power is applied, the first LED on the left lights up, since the first instruction lights it. Fantastic! Okay, so we have 3 output lines connected to LEDs. We could use those lines to address 8 LEDs using a 74138 3 to 8 line decoder. We can connect the 3 LED output lines from the flash chip to pins 1, 2, and 3 of the decoder. Pins 4 and 5 need to be low, and pin 6 needs to be high to enable the output. And the LEDs will connect to pins 15, 14, 13, 12, 11, 10, 9, and 7. What this will do is convert the binary value present on pins 1, 2, and 3 to select a single output on the pins connected to the LEDs. Let's write some code to get the LEDs to start from the bottom to the top and repeat down to the middle. Now, notice that the LEDs are inverted. That is, they're all lit except for one. We could solve this using a 74238 decoder, but we don't have any of those in DigitalWorks. So we could either create a new chip or just add inverters to the LEDs. Here is a new 238 chip that I created by copying the 138 and adding inverters into the macro right here. Now this works as expected. I also happen to have some real 74HCT 238s, so we can actually build this up. And I'll just reprogram this flash chip. There, let's test it. Perfect! So, in this video, we had some fun successfully building a homemade single-chip 74 series logic CPU. I'm going to make one more video on this Plague Mark I CPU to demonstrate solving our original problem with additional ICs instead of changing out the counter chip. This will allow us to keep the original 74393 chip and still have a working circuit. Then after that, I plan on moving on to the next CPU, the Plague Mark II. The Plague Mark II will add a lot more functionality, including the ability to do some calculations and make decisions based on those calculations. We'll be getting a lot closer to the functionality of a real CPU. So stay tuned for those future videos. Thanks for watching, and I'll see you next time, right here on Dr. Plague.